Okay, so as I'm saying a while ago, so this is now our R total and then the I total. So 11.2 divided by 2.8 will give us a value of 4 amps. Okay, and what else? Well, actually, those are the only things that we can solve after getting the uh, Thevenin equivalent circuit. Okay, so mostly the question right here is what is the current that is flowing on the R load. Okay, or we can actually also get the voltage drop across R Thevenin and then the voltage drop across R2. Okay, so we are going to get the VR2 right here. So we need the I total, which is 4 amps, and then the value of R2. So I total is 4 amp times R2, which is 2 ohms. So the voltage drop across R2 is 8 volts. Okay. And then for the current on the R2, well, of course, it's the same with the I total since we only have one circuit, one flow of current since they are in series. So yeah, there you go. So were you guys able to follow so far?
Yes, sir.
All right. Okay, there's a question. So sir, saan po ulit nanggaling yung 0.8? This 0. Oops, where's my cursor? This 0.8 right here came from our first solution, the RTH right here. So again, in order for you to get the RTH, so you need to find where the R load is. So in here, the R load is in the middle. So this is where we will put the node A and node B. So it's like V, no, not BRB, RAB, okay, resistance across AB. So we transform this one into this one, and then as you can see, Mr. Janelle Agustin. So we have here a parallel connection of your R1 and R3. Okay, so that is why we have this formula right here. So 4 divided by 5 is equal to 0.8 ohm. Okay. All right. So again, the very very important thing that you guys need to know. I mean, not need to know. Need to remember. Okay. So find the RL first because that is the part. Okay. We always note that one as node AB. Okay. So if it's on this position, then that is a node AB. Sometimes the RL is also in right here. So we put that one as our node and then B. Okay, so node AB. So that is where you can find the oops. That is where you can find the RTH, okay, and then the VTH. Okay, and then once you're done in solving for those two, then you can now transform that one into Thevenin equivalent circuit. And then just put back the R load right here. And then you can now solve for the total resistance, total current, and then the voltage drop across R2, and then even the voltage drop across the R Thevenin. Okay, so any other questions so far? None? I guess none. Okay, so going back to our module, so again, these are just explanations that, on how to get the RTH and then the VTH. And then here are the answers. So we have here the total, oops, yeah, the total final voltage, knowing that we have that flow of current, so 28 minus 7 is of course 21. And then the current that is flowing on the entire circuit, which is 4.2, which is the same with our value right here, 4.2 amps. So this is point, okay? And we have here the individual resistance, the 4 ohms on the R1, and then the 1 ohm on the R3, and then the final ohms, okay, once you have combined those two, okay, which is 5 ohms. Okay, but take note, this is not our RTH. This is just the final total resistance, okay, when you combine those two. All right. So this is the final circuit also of our uh, circuit right here. Okay, with just a label. So the 4.2 amps flowing on the entire circuit, and then the 11.2 volts, which is our VTH, and then the RTH, which is zero point 0.8, and their labels for the polarity, right? So there you go. And then for the RTH right here, which is zero point 0.8, and then the final Thevenin equivalent circuit, and then you can now solve for the R total, okay, which is 2.8 for the Thevenin equivalent circuit, which is now this one, 2.8, and then for the I total, which is 4, okay, which is just the same with this one, 4 amps, and then their individual resistance, so zero point 0.8 and then 2, combining those two will give us 2.8 uh, total resistance. All right, so if this is not enough, you can visit other sources like NASO Academy, Khan Academy, what else? All About Circuits, Circuit Globe. So there are many other, what do you call this one, article or website which teach the basics of Thevenin circuit. Okay, and then if those things are still not enough, you can check this one. Okay, this is a YouTube link. Okay, this is an English video example, and for those who cannot understand, I mean, if you're a foreigner, then you can go with English video example. Okay, but if I cannot understand, like, ang gulo. So if you're a uh, foreigner, then go for English, okay, because you will not understand anything in Tagalog with example. But if you're a Filipino, then you can go with English or Tagalog. But if you cannot understand the way of this guy explaining things, then you can always go with this Tagalog with example. Okay, so let me just show this one to you guys. All right, so just wait a second because we have ads as always, and then another ads.
Hi guys, opening current source. So circuit.
Okay, so as you guys can see right here in this example, we have three different values of RL. So the first one is 6 ohms, the second one is 16, and then the third one is 36. Okay, so this is a variable resistance. So when we say RL, again, load resistance, that is always, we always, put our devices or our appliances. So let's just say that this is a TV for now, and then you want to solve for the, your electricity, uh, we call this one, electricity, electricity fee, yung binabayaran natin sa kuryente, yung ganun, basta yung power. Okay? So, just apply Thevenin's theorem, and then, even though this one will change, let's say, before this one was TV, and then right now this one became a refrigerator, which has a higher resistance or load resistance, then you can easily solve for that one. Okay, just replace the RL. After solving for the VTH and then the RTH. Okay, so that is the main advantage of the Thevenin uh, circuit. Okay, or the Thevenin theorem. Okay. So yeah, because
Tapos,
if
hanap
you don't have this RL right here, then you have to redo everything. Okay, like if this one change, you have to start from the very start and then solve for the total current again, solve for the current that is flowing here, the voltage drop, etc., etc. But if you have Thevenin's equivalent circuit, then you can just simply replace the RL and then solve the total current again, and then solve for the total resistance, etc., etc. Okay, so yeah, I hope I was able to give you guys the importance of the Thevenin's theorem. So, are we clear so far? Or you guys have a question in mind that you would like to ask? Question? Mr. Jasper, Miss Jade, Mr. Lawrence, Ryan, John David, Mr. Rava, Miss Kate, Mr. Janelle, Mr. Carl, Carl Jan, Mr. Bradley, Miss Maxine, Miss Mark, Mr. Kenji. Okay, you guys sure? All right. So if you guys don't have a question anymore, then we can now proceed to the next example. Okay. So before that, let's just have again a review. Okay. So again, the Thevenin theorem is a way to reduce a network to an equivalent circuit composed of a single voltage source. So you need to have the series resistance and then the series load. Okay. And then steps to follow for the Thevenin's theorem. So find the Thevenin source first. So either of those two, you can find the Thevenin's resistance or the Thevenin source. So it's fine as long as you will get those two. Then after that, then you can now transform the original circuit into that Thevenin equivalent circuit. Okay, and then after that, you can now analyze the voltage and current for the load resistor following the rules for series circuit. Okay. So yeah, the reference for my slide 1 up to slide 13 is all about circuits. Okay, and then the next one right here came from another source or another website. So basically, you have the same method. It's just at a different value. Okay, so just again a different explanation, but mostly it will give you the same concept. Okay. So let's have another example from another website. So Thevenin's theorem is especially useful in the circuit analysis of power or battery systems and other interconnected resistive circuits where it will have an effect on the adjoining part of the circuit. Okay, so again, it will lead us to the same circuit wherein we have the Thevenin's voltage, wherein in here it's just Vs, and then we have here the Thevenin's resistance, wherein in here it's just called RS, so just a different naming. But for the RL, it's still the same. Okay, and again, as far as the load resistance RL is concerned, any complex one-part network consisting of multiple resistive circuit elements and energy sources can be replaced by one single equivalent resistance. So take note that in here we call that one RS, but on the all about circuits we call that one RTH. So those two are just the same. So RS is equal to RTH. Okay, so the same with this one single equivalent voltage VS. So in here we are calling that one VH. I mean VS, but on the first example, we are calling that one VTH. So those two are just the same. So VTH is equal to VS. Okay. So RS is the source resistance value looking back into the circuit, and VS is the open circuit voltage at the terminals. Okay. So we have a similar example, but just different values. Okay. So basically the same method. Okay, on how to get the RS and then the VTH. So in here you have to remove the resistance and then short circuit the sources. So again, if it's a voltage source, then you have to short circuit that one, just like what we did right here. Okay, so we'll short circuit and then open circuit for the current sources. Okay, and there you go. That is the first step in solving for the RS or RTH. So as you guys can see, they are in parallel with each other because we have our node A and B right here. This is where we are going to solve for the RTH. Okay, so just apply the formula of the parallel for the R1 and R2. Okay, so it will give us 20 times 10 divided by 20 plus 10 will give us 6.67 amps. So this is already our RS or our RTH. Okay, and then after that we can now find the equivalent voltage or the VS or the VTH. So in here, we are assuming this flow of current because as you guys can see, this one has a larger value than this one. So basically, this will dominate the entire flow of current. Okay. So from here, we can apply Ohm's law again or KVL. Okay, just for you to solve for the current. But in here, we just simply applied the formula, okay, of the Ohm's law, which is I is equal to V divided by R. So in here we have 20 minus 10 divided by 20 plus 10 because they are in series connection right here. Same with this one. So 20 minus 10 because they have different polarity. Okay. Then after that you will get 0.33 amps. Okay. So from here you can now solve for the VAB. Okay. So again, our VAB could be on the left side or right side, so any of those two will do. So it will give you the same result, okay? So it will give us 13.33 volts and then 13.33 volts. So this is just a different method and then another method, okay? So can you guys follow up to this point? Hello, hello. Are we still clear? All right. So I would like you guys to confirm this one. Okay, once you are trying to try to understand this one again. So I would like you guys to retry and try different method like maybe KVL. Okay, if you will get the same current. Okay, and then after having that one, then you can now apply just like what we did a while ago right here for the left side part and then the right side part just by getting the potential voltages. Okay, and then it will give us 13.33 volts. Okay, so yeah, in that way you'll be able to verify or confirm that you can use this method or Kirchhoff's method or via potential voltage method. Okay, and then once you're done in getting the VTH and then the RTH, then you can now transform that one into Thevenin's equivalent circuit. Okay, so 13.33 right here and then 6.67 ohms right here. And then just put back the value of your RL. Then from here, we can now solve for the final total current, which is 0.286. So just apply Ohm's law, V divided by R. Okay, so 13.33 divided by the total resistance, which is 6.67 plus 40 ohms. So it will give us 0.286 ohms. Okay, and as a conclusion, so Thevenin's theorem can be used as another type of circuit analysis, okay, just like superposition, nodal method, and many more. Okay, that is particularly useful in the analysis of complicated circuits consisting of one or more voltage or current source and resistors that are arranged in the usual parallel and series connections. So while Thevenin circuit theorem can be described mathematically in terms of current and voltage, it is not as powerful as mesh current analysis or nodal voltage analysis in larger networks because the use of mesh or nodal analysis is usually necessary in any Thevenin exercise. Okay, so it might as well be used from the start. However, Thevenin's equivalent circuits of transistors, voltage sources such as batteries, etc., are very useful in circuit design. Okay. And in here, there's another summary wherein Thevenin's theorem can reduce any complicated electrical network into a simple circuit consisting of one single voltage source and then one Vs, which is in series on a single resistor, which is our R load, okay, and Rs. Okay. So when looking back from terminals A and B, the single circuit behaves in exactly the same way electrically as the complex circuit it replaces. So that is the IV relations at terminals AB are identical. All right, and then again the summary for the steps. Okay, so again the first step is removing the RL, and then you can now find the RS or the VDH. Okay, and then you can now transform that one into Thevenin's equivalent circuit, And then you can find the current that is flowing through the load resistance. Okay. And then for my reference for this one came from electronics tutorials. So just click this one and then it will lead you to their website. All right, so yeah, that's it for the Thevenin's theorem. Any other questions so far before we proceed to the Norton's theorem? So anyone who's confused and maybe would like to confirm something, verify something. Okay, so none for now. Okay, so again, we have a lot of websites. So this module right here has two different sources. So the first one is all about circuits, and then the second one is electronics tutorials. So you can also visit again Khan Academy, Neso Academy, Circuit Globe, or if that is not enough, then you can always visit some YouTube tutorials wherein this one is super useful. This guy right here, the engineered Matt, so his tutorials are super on point, okay, on why we are using that theorem, okay. So in here we also have an example of the current source, okay, in which you will know everything once he's done converting this one into a single voltage source and then the RTH and then the RL. All right.
Hidden resistor.
So make sure to check this video right here. Okay. All right. So I guess that's it for the Thevenin's uh, module. So just let me know if you have a question again before moving on to the next module, which is Norton's theorem. And if none, just give me a thumbs up so that I know that most of you were able to get the idea or the concept of the Thevenin's theorem. Right, so 1, 2, 3, 4, 5, 6, 7. What about the others? 8. What about you, Mr. Mina, and then Miss Maxine? Who else? Mr. Ryan, Miss Jade, Mr. Raba. Alright, so maybe they're not in front of their computer. Anyway, so yeah, that's it for the Thevenins. And if that is not enough, well, you can visit this one maybe if I have uploaded a different tutorials. Well, in here, alright, okay. So the same video materials, so the English version and then the Tagalog version. In here, it's just an additional explaining the dependent and independent sources. All right, so let's check the other tutorials in here. If there is a new method, then you might want to check that one also. So moving on to the next module, which is the Norton's theorem. So once you've learned the concept or the idea of Thevenin's theorem, understanding the Norton's theorem is super easy. It's like, once you're done in understanding this Thevenin's theorem, you have already understood 50% of the Norton's theorem because they have similar concept. Okay, just in some ways they're different. Okay, so without a further delay, let's now move on to the Norton's theorem. So Norton's theorem is again another method to simplify any linear circuit, no matter how complex it is. Okay, So in here, it will convert it into an equivalent circuit. So again, we have another conversion, but with just a single current source and a parallel resistance connected to a load. So in here, we have a single current source. In Thevenin's theorem, we have single voltage source. And in here, we have parallel resistance. But in Thevenin's theorem, we have a series RTH. Okay. And then the rest are the same. Okay. Especially with the RL. All right. So they just have different sources. Okay, so RTH voltage. I mean RTH. For the Thevenins, that's voltage. For the Norton, that's current. Okay, so basically the same. This is only possible if there is no exponents or roots. Okay, must be purely linear. All right. So we will use the same example. Okay, and then we have to verify whether the calculated value from the previous method is the same by using this method, the Norton's theorem. So before we have series connection, but in here we now have a uh, parallel connection. Okay, so we have here the current source, and then we have here the R Norton. Okay, or the Norton's equivalent. But we still have the same load, which is on this right side right here. Okay. So without a further delay, let's try to solve this one. Okay, let me just copy this one and remove everything, and then paste it right here. There you go. Okay, so basically we have the same steps. So remove RL, just open circuit that RL, and then find the I well we can call that one Norton's resistance. Okay, not uh RTH anymore. And then for the VTH, so it's not VTH anymore. So it's now uh, Norton's current, or IN actually, or this one is RN, Norton's resistance. And then right here we have Norton's current, or IN. Okay. And then once you're done in getting the RN and then IN, then you can now transform that one into Norton's equivalent circuit, and then you can now solve for the unknowns, total voltage, voltage drops, etc., etc. Okay, so first step is we have to remove the RL, or make it open. Okay, then after that, we have to short circuit everything. Okay, or remove the sources. So short circuit for the voltages, and then open circuit for the current. So remove this one, and then remove this one also, and then short circuit is one, short circuit is one. And then we can now find the RTH right here. Wherein this is now our node A, and then this is our node B. So looking for the uh, total resistance across RTH, so we have to transform that one into this kind of circuit. So this is our node A, this is our node B. So 4 ohms right here, and then 1 ohm right here. So as you guys can see, we'll get the same result. So R1 times R3 divided by R1 plus R3. Okay, this is a mistake, not RTH. This is not RTH also. RN. Okay, Norton's resistance. Okay, and this is also RN. Right? So R1 is 4 ohms, and then R3 is 1 ohm, and then R1 is 4, and then R3 is 1. So 4 times 1 is 4, and then 4 plus 1 is 5. So 4 divided by 5 is still 0 0.8 ohms. So of course, nothing will change since we have the same values. And after that, you can now solve for the VTH. Okay. Ah, why VTH? Still using the Thevenin's method. So in here, we now have to solve for the IN. Okay, the Norton's current. So the same method, we have to find the final current that is flowing right here. So instead of Rn, we are now looking for In right here. So as you guys can see, we can actually apply KCL or KVL right here. So going in and then going out. Okay, but in order for us to solve for the value of the IN right here, we have to apply KVL, okay, and then we need to know the values of your voltages right here. So basically, it's just the same step, just like what we did a while ago in Thevenin's circuit. So let me just replace this one again. There you go. So removing this one and then solving for IN. So in here, we can assume that we have the same flow of current since this will basically dominate this voltage source right here. So again, we have 28 minus uh, I times 4 and then minus I times 1 and then minus 7. Okay, is equal to 0. So 28 minus 7 is again 21 and then minus 4 plus minus 1 is negative I 5 is equal to 0. And then you can transpose this one on the right side. 21 is equal to I 5 and then you can now find the value of our Norton's current. So I is equal to 21 divided by 5. So 21 divided by 5 is equal to 4.2 amps. Okay, so that's actually already it since we don't need to find the total voltage across this one. Okay, or the final potential voltage. So we only need the total current, which is your IN. Okay, so from here we can now transform this one into Norton's current or equivalent circuit. Norton's current. Norton equivalent circuit, not Norton's current. So let me just copy this one and then paste it right here. So I Norton is 4.2 and then R Norton is 0.8. Okay. And then from here we can now solve for the value of we can now solve for the value of final voltage, okay, or V total. So of course we need I total times the R total. So I total is already 4.2, but for the R total we have to solve that one, okay. So R total is R Norton in parallel with R load. So that's 0.8 times 2 divided by 2 divided by 0.8 plus 2. Okay, so 2 times 0.8 will give us 1.6 and then 0.8 plus 2 will give us 2.8. So 1.6 divided by 2.8 will give us a final total resistance of 0.571 ohms. Okay, and then we can now use this one to replace this RT right here. So again, V total is equal to I total, which is 4.2 times R total, which is 0.571, will give us times 0.571, 2.398 volts. Okay, and then from here you can also solve for the voltage drop across R Norton and then the voltage drop across R2. Since we already have this current right here. Ah, but before you can do that, so you have to know the current that is flowing right here first before you can solve for the voltage drop across R2. So you need to get the final, I mean not final, the current that is also flowing here because they will split into two. Okay. But anyway, let's see what are the unknowns for this one. So in here we have 14 amps. Why do we have 14? Ah, I see.